In the first part of lecture 8, we will talk about a technique that we can use in double integral, which is to convert everything into polar coordinates. So let us review the relationship between Cartesian coordinate and polar coordinate. So on the left, I have a Cartesian coordinate, which is the usual xy plane. And as you already know that in the Cartesian coordinate, you can tell position of a point by moving left, right, or up, down. So for example, if I want to go to the point 3, 3, I could move 3 unit to the right, then 3 unit up. That's how we would describe a position of a point in Cartesian coordinate. We move along the x grid or the y grid. But in polar coordinate, instead of having x and y, you would have r and theta. Theta tells you the direction that you have to look into or have to go to, and r is the distance in that direction. So for example, let's still consider the point 3, 3. I want to go to the point 3, 3, so I will look at the angle pi over 4. Theta will tell me the direction. And how far do I have to go in this direction is given by 3 square root 2. And the way we compute 3 square root 2 is just using the right triangle to compute the hypotenuse. So to go to the point 3, 3, we would look at the direction pi over 4 and then walk a distance of 3 square root 2. So comparing to the Cartesian coordinate, we would have theta describe the angle, and the ray r, which give you the distance, how far you have to go in a certain direction. And the relationship between the two coordinates is given by the following relationship. I know that x squared plus y squared should be r squared. And tangent of theta is given by y over x. So if you want to solve for theta, that is the inverse tangent of y over x. That's how you can go between the two coordinates. So the Riemann sum for the polar coordinates when you do double integral, this is really well described in the lecture note as well as the textbook. So I will skip that part and I will go straight into examples and the main ideas of using polar coordinates. So the idea for using polar coordinates in double integral is actually quite straightforward. Because in double integral, we integrate with respect to the area. And some regions or some curves are particularly suited for using polar coordinate. For example, if you want to integrate over a region that looks like a circle, then a circle can be really easily described in polar coordinate as r equals to a constant, right? Because a circle has a fixed radius. So instead of using x squared plus y squared equals r squared in Cartesian coordinate, we can describe the same circle very succinctly by just saying the radius equals to a constant, to a positive constant particularly. Or if you have something that looks like a rose petal, a parametric curve, in Cartesian coordinate, the equation for this rose petal would be quite lengthy. But in polar coordinate, it can be described by r equals to a cosine n theta or a sine n theta, depending on how many petals we have or what is the orientation of this flower-shaped curve. So some regions are easier to describe in polar coordinates. And if we're in that case, then we want to convert from Cartesian coordinate into polar coordinate because that will help us simplify a lot when we do the integral. So the idea is that if you have a radially simple region, And what do we mean by radially simple? It means that your angle is bounded between two constants, and the radius r is bounded by two functions dependent on the angle. So if your region can be discretized by putting the polar grid on it, then it's convenient to use polar coordinate. And I will show you a few examples to describe when it is convenient that you should use polar coordinate. So the idea is the following. In Cartesian coordinate, you have a region R, and you want to integrate over this region with respect to the area. If the region R is suited for polar coordinates, then you will parameterize your x into r cosine theta and y into r sine theta. Right, so x is r cosine theta and y would be r sine theta. Then the area dA is now turning into r dr d theta. So dA is now r dr d theta. And it is the common mistake to forget the r when you translate dA into, it should be r dr d theta, not just dr d theta. So do not forget about this r here. And once you do this parameterization, you would have a double integral in polar coordinates. And the technique we use for doing double integral will be the same. You still have to write this as an iterated integral by using Fubini's. So let us look at one example. So I want to find the volume under the hemisphere given by z equals to square root of 1 minus x squared minus y squared. Above the region bounded by x squared plus y squared minus y equals 0. So first, we have to plot the region. And there is a little trick to manipulate this region into the familiar form that we already know, which is to complete the squared. So I will complete the square. In this equation here. And this part I could write as x squared plus y minus 1/2 quantity squared and move the negative 1/4 to the other side. Which is the equation for a circle center at the point 0, 1/2, radius 1/2. Right, so that is a circle that I drawn on the left. So this in polar form. So all of this is complete the squared. And in polar form, this is the same as r equals to sine theta. I mean, it is clear in this case that we could use polar coordinate because a circle is a radial region. So what happens if we want to convert this into polar coordinates? Step 1 is we plot the region and then we write it in terms of polar coordinates. Now we have to convert the surface of the function that they given to us into polar form. Remember that x squared plus y squared is r squared. So instead of z being square root of 1 minus x squared minus y squared, we could write z equals to 1 minus r squared. So the integrand now can be written as square root of 1 minus r squared. dA is r dr d theta. The only thing that we have to worry about now is how can we describe the bound in radius and in angle theta for our new polar coordinates double integral. So as we did in the last step, the radius is described by the polar curve r equals to sine theta. So here the radius will be going from 0 to sine theta. Because we're doing the integral in terms of r first. Now for theta, how do we decide what is the range of theta? So what is the range of theta? This you need to plot the curve. So to work this out, you need to plot r equals to sine theta and see what is the range of theta that will give you a full circle. So you have to do the following. Pick theta and r. So your theta could be 0. Choose the special angles to make it easier on yourselves and so on. And because this is the circle is a closed curve, so once you start from theta being 0, radius is 0. Once you return to 0 again, that is one closed curve. So then in this case, if you plot it out, you will see that your theta is going from 0 to pi. So this is the conversion from Cartesian coordinate to polar coordinate. So let us try to integrate this polar coordinates double integral. So the integral we want to do is 0 to pi, 0 to sine theta, square root of 1 minus r squared, r dr d theta. So we will do this as an iterated integral, which means that we'll do the inside first. So you do the integral in terms of r first, then you integrate with respect to theta. And for this integral in terms of r, this is a u sub problem. So if we say u being 1 minus r squared, then du is negative 2r dr. So the outside integral is in terms of theta, so we'll leave it alone and focus on the r integral first. When I convert r in terms of u, I will have the following. So u to the 1/2, r d theta is negative 1/2 du, so negative 1/2 du, and I will have a new bound in terms of u. When r is 0, u is 1. When r is sine, 1 minus sine squared is cosine squared. So after u sub, we will have the following. So now let's integrate. When we integrate in terms of u, the negative half is a constant, so we can bring it along. U to the 1/2, we find the antiderivative, so this will be 3/2. I have a 2 over 3 here, and evaluate it from 1 to cosine square theta. So what we have now will be the constant you can simplify and have negative 1/3. Then we will do evaluation. So cosine square theta all to the power 3 over 2 minus 1 d theta. And there is one thing that we have to pay really close attention to in this step. So if you look at the term, this term and the bound, you have to pay attention to those terms. Why is it important to be careful in this case? Because I have cosine square of theta, then raised to the power 3 over 2, which means that I have the square root of cosine square theta all to the third power. That's what the power 3 over 2 means, right? You take the square root, then you raise it to the third power. And what is square root of cosine squared? It is actually absolute value of cosine theta raised to the third power. And theta in this case, from the bound, you can tell that it's going from 0 to pi. And cosine between 0 and pi is not all positive. So this is cosine of theta. Right, so the absolute value of cosine theta when theta is going between 0 to pi, it would, because cosine changes sign, right? So you have to be very careful when you do this step. There must be an absolute value when you do the square root of cosine squared. So in order to deal with this square root, it will be best if we break the integral from 0 to pi to 0 to pi over 2, and then pi over 2 to pi. So 0 to pi, negative 1/3. Let's just bring it outside. Here we already work out that it will be cosine, absolute cosine cubed minus 1 d theta. We will break it into two pieces to deal with the absolute value. Go cosine to pi over 2. Plus pi over 2 to pi. And from the plot of cosine theta, you can see that from pi over 2 to pi, it's negative, right? So you have to deal with the absolute value at this step appropriately. So expand this out. Cosine pi over 0 to pi over 2, cosine is positive. So absolute value of positive cosine would just stays the same. Plus, from pi over 2 to pi, because cosine is negative in this range, here, absolute value of a negative number, so you would have negative of that. So it would be negative cosine theta cubed minus 1. So then you can integrate it normally from this point on. Because the only important part for this question is that we have to be careful about the part where you have absolute value of cosine, and because cosine is going from 0 to pi, you have to split the region up into two pieces. Or if you read the textbook, this is example 3 in the polar coordinate section, and they use symmetry to convert or to change the angle, the bound from 0 to pi over 2. But again, when you do polar coordinates, because of the sign change of sine dependent on the interval of theta, your cosine could have plus or minus value. So if you do the square root of cosine square or something, you have to be careful with the absolute value here.